So in this video, we're going to be talking about the how we're going to be able to use specific heats in calculations having to do with materials. Talking about how a certain amount of heat that's absorbed by an object would result in its temperature changing. All right. So first, a little bit about specific heats. All right. So first of all, let's recall what specific heat is. All right. It's the amount of heat that you have to put into something to get 1 gram of that material to rise by 1 degree Celsius. All right. One way, just really quick thing to remember is water has a very high specific heat. And if you think about the way water behaves, it is actually relatively hard to get water to change its temperature. All right. If you think about like a pool in the springtime, it's got to be hot for a long time to get that pool water to warm up. All right. And that's because water's got a high specific heat. It requires a lot of heat to get that temperature to change. All right. The opposite's true in the fall. It's got to be cold for a long time for its temperature to drop. All right. Water tends to lag behind whatever the air temperature is because of its specific heat. All right. So let's move on to using these specific heats in calculations. All right. First of all, some notes about specific heats. Different materials have different specific heats. All right. For example, water has a different specific heat than oil. All right. Copper has a different specific heat than aluminum, for example. All right. So the place that we're going to be able to find values for specific heats is on your reference guide. All right. If you look on this page right here, these are all the specific heats for these different metals. All right. So one thing I want to note about these is the state of matter is assumed to be solid for all of these because we're assuming that we're dealing with these at somewhere close to room temperature. The only material on this that's not assumed to be a solid would be mercury. All right, and that leads to the next topic, which is the fact that states of matter, depend on the phase of whatever the material is. All right. Liquid water has a different specific heat than solid water. All right. And when we say solid water, what we mean is ice. All right. Even though they're both H2O, all right, they're both chemically the same thing, the state of matter is going to have an effect on this property, which is specific heat. So when you're taking a look at this reference guide here, notice that there's actually 3 different specific heats for water. One is for water in its ice form. This one is going to be water in its gas form, which they say is steam, but really it's just water in its gas form, like humidity in the air. Yeah, that water would use this value right here. All right, but then if you have water in its liquid form, it's going to be 4.18 joules per gram per degree Celsius. All right, so you need to make sure that when you're doing a problem, you're aware of what state of matter that would be at when you're doing the calculation. All right, so let's take a look at the equation that we're going to use here. All right, so the equation that we're going to use is this one right here. Q equals mCp delta T. All right, Q stands for heat either absorbed or released by the material. All right, you can do it if something's absorbing heat. For example, if you put an object into a flame, all right, it's going to absorb heat from the flame. That's going to cause its temperature to rise, which is going to be reflected in this thing right here, the change in temperature. All right, Q could also be heat that's given off by the material, all right, heat released by the material. All right, for example, if you put something into a freezer, heat is going to flow from the object to the surroundings. So Q could be the amount of heat that an object loses, and in that case, it's going to cause the temperature to go down, all right, which is going to be reflected in this delta T right here, which is the change in temperature of the material. All right, so, all right. M is going to stand for the mass of the material. Because if you're saying, I'm going to put this much heat into a material and see how its temperature changes, the amount of the material that you're talking about matters, all right? If you take a candle and you put a teaspoon of water over top of the candle, it's going to cause that water's temperature to change by a lot, just because there's so little of that material that if you give it that certain amount of heat, since there's a very little amount of it, its temperature is going to go up by a lot. If you did the same thing with a gallon of water, all right, put it on top of the same flame for the same amount of time, its temperature is not going to go up by nearly as much. All right, so mass is going to have an effect on this equation. All right, CP is the specific heat. All right, again, that's that property of a material that describes how a certain amount of heat is going to cause its temperature to change. All right, remember, materials that have high specific heats require lots of heat in order to get a temperature change, whereas materials that have low specific heats, you can give them a little bit of heat and their temperature will change by a lot. All right, so and the place that we're going to find these specific heat values are going to be in your reference guide. All right, so when you look up a material, if it says you're dealing with iron, you're going to use this value right here. If it says you're dealing with water, you're going to use, or liquid water, you're going to use this value right here. You just need to read the word problem and figure out the appropriate value to use. The last term in the equation is delta T, and that just stands for change in temperature. All right, and so in these problems, you're just going to have to use a little bit of reasoning on this. All right, if something is absorbing heat, you can calculate this delta change in temperature. That's going to be how much the temperature would rise by. All right, if the material talks about something releasing heat, you're going to calculate a delta T. That's how much its temperature is going to go down by. All right, so you have to read into the details of the problem and see what the appropriate thing to do would be. All right, so let's take a look at a sample problem. How much heat must be absorbed for 14.3 grams of liquid water to cool from, sorry, that should be to warm. Okay, well, let's just go and leave it cool from 87 degrees Celsius to 25 degrees Celsius. All right, so what can we figure out from this problem? All right, so it says how much heat. All right, that's Q. All right, that's what you're going to use to represent that. All right, remember, that's a form of energy. All right, it's not the same thing. It's related to temperature, but it's not the same thing as temperature. All right, how much heat must be, actually, this should be released. Let me change that since it's cooling down. All right, for this much water to cool from 87 to 25. All right, so we can calculate a change in the temperature. That's just the difference in the temperature here. This is obviously the mass right here. And one thing that's relevant is we're talking about liquid water. And in this problem, we use the term liquid water, but you should be able to figure out even if it didn't say liquid water, because if water is at 87 and going to 25, and we're not just talking about regular water in a room, we're not, doesn't say anything about the pressure, which we'll talk to why that matters. If you remember the phase diagrams, the boiling points of water depends on pressure. We're just assuming this is normal atmospheric pressure. So you should know that this would be a liquid at in this temperature range. All right, it's not nothing is greater than 100 degrees Celsius and nothing is lower than 0 degrees Celsius. So the delta T is going to be 62 degrees Celsius, and this is going to be our specific heat. So we're going to take this equation right here, mCp delta T, and you plug in for your mass, you plug in for your specific heat, you plug in for your change in temperature, and you do your math, and this would be the number that comes out. Notice that I have rounded the number to 2 significant figures because 62 degrees only has 2 significant figures in it. So these problems can be asked in several different ways. So here's another example right here. 17 grams of gold at 25 degrees Celsius absorbs 180 joules of heat from a flame. What would be the final temperature of the gold? All right, so one thing that tells us that we are going to use this equation, Q equals mCp delta T, is that we are talking about something where the state of matter is not going to change. All right, if you've got gold at room temperature, it's got to absorb its temperature's got to go way higher before it would ever melt. All right, so we know that what's going to happen here is the temperature is going to change while it's staying at a constant state. All right, it's going to go from a colder solid to a hotter solid. All right, and that's when you use this equation right here. So let's see what we can label. All right, so some things that we can pull out from this problem. 17 grams, that's going to be the mass. That's going to be M. All right. This 25 degrees Celsius, that doesn't exactly correspond. That's the initial temperature. All right. It's at, which I'm going to represent as Ti. All right. It's asking what the final temperature would be, and I'm just going to represent that as TF. All right. We're just going to leave that there for right now. It absorbs this much heat. All right. You know, heat is Q. All right. That's the amount of energy that it's going to get from that flame. And so when we're looking through this, is there anything else that we could get? All right, there's one more thing that we can get from this problem, and that has to do with the fact that we know the material. All right, gold. All right, if it's at 25 degrees Celsius, it's going to be solid gold. And if it's gold in its solid form, we know that its specific heat is this value right here. So let's go through this problem. I know Q, I know M, I know Cp. The only thing I don't know is delta T. And if I've got one thing that I don't know, I can solve for that. So first thing, I'm just going to rearrange this equation to get delta T by itself. And then I'm going to plug in the values for this. So if you plug those numbers in and then calculate the answer, notice when you cancel out your units here, the only thing that's left is degrees Celsius. And I round it to 2 sig figs, 82 degrees Celsius. Okay, so keep in mind, this is not your final answer, because what that represents is your delta T. That's how much your temperature would change by. So how would you figure out what the final temperature is? Well, if your initial temperature was 25 and it absorbs heat and its temperature goes up by 82 degrees, that means that the final temperature is going to be 107. All right. So the next type of problem, 232 grams of an unknown metal at 25.0 degrees Celsius absorbs this much heat, causing its temperature to rise to 39.2 degrees Celsius. What is the metal? All right. So let's see if we can figure this out. So let's identify what we know from this problem. This is going to be our mass. Delta T, we know that its starting temperature and we know its final temperature, so we can calculate a temperature change. All right, it tells us how much heat is absorbed, so we can just write that down. The only thing in this equation that we don't know is Cp. All right, and if we can calculate the specific heat, remember that's a property of a particular material, and all that we have to do is go back and compare it to these numbers right here, and we could figure out which material that is. All right, so rearranging for specific heat, we get this expression right here. And then we can take these values and plug that into that expression, calculate our value, and we get a specific heat of 0.522. But notice what it says, what is the metal? All right, so what we're going to do to figure that out is we're going to say, well, if we know that this is that property, that the specific heat of that unknown material, we're just going to compare it and see if we can find that on this list. And even though it's not exact, it's really, the one that's by far closest to is this one right here. So that's going to mean that our material is titanium. All right, so good luck on the practice problems.